Hi, my name is Ashot, and today we're going to talk about trie-trees. So trie-trees or prefix trees are widely used in word dictionaries. And after today's lesson, you'll have much more better understanding in search engines auto-completion operation such as Google search, right? So we'll talk today about trie-trees and their basic 3-4 operations named like insert, search, of course. We'll have two operations with search. It will be search a word and search a prefix. So we want to understand if there is any word which starts with some prefix, and of course the delete one, probably the hardest one in every tree operations. Yeah, so we'll start with insert, and actually we'll try to figure out how this trie-tree nodes, as you know, every tree has some nodes, how we implement them, and we'll understand how these trie-tree nodes are constructed and what they have inside them. We'll try to write the node and all the operations in pseudocode manner. So the node will have a hash map. Keys will be characters actually, and each character will look at some other tree node. So we'll understand how it works a little bit later. And another member will be a boolean of is word or not. Of course, we can keep here some count, like how much the same word occurred in some text or not. But the basic node construction will have only this hash map of children, and is word boolean indicates if we have this word in our text or not. Okay, so for example, I have ABC string, right? And I want to insert in this trie-tree. How I do that? So in our root, we'll have this character A. I'll put it false here. I'll explain later what is it. Now I want to insert this B. So I mean that I have another node and my A is looking at this B. Right? Okay. And the C1. Let me explain what I've just done. So I have this A character here, and I put it in the root of the trie-tree. Then I say, you know, this character A will look at another node, which we've constructed here, and in that node's children, I'll put B, character B. And for the same operation, I will do for C character. So in these node's children, I will have B, which is pointing to a node, a new node, and where I will put the C character. After that, I will create another new node and tell that C will look at nothing. Actually, not nothing. It will be some node which will indicate the is word. So I mean that A, B, C will end up the empty children's node, a node which has no children, but it will indicate that this is the end of the word, okay? And you can see that we have these multiple F's here. What are actually pointing out that, for example, if we have this A in our trie data structure, we'll put this true here, indicating that we have an A word, which is an end of any word, okay? So just keep in mind that we have this like finishing node, which is actually telling us if we have a word here or not, if it is an end of the word or not, okay? Let's just put another word, AB, for example, EF. We'll try to insert this string here. So we'll take this A. Actually, at first, we'll try to understand if we have the first character in our root or not. if we do have, so we take this A and go to its node, like what the value of the key in the hash map is. So the node will be this one, which keeps B and F here. Okay. So now we try to understand if this hash map has this B character here or not. And we see that yes, B is in the children of this current node. So we go from this character to its value, so here. And we'll try to understand if E, the same operation. So each time we want to understand if the character from the string exists in the children or not. If yes, we just go through the keys to its value, so to the node, and try to find if their children keeps this character or not. So when we come here, we do see that E is not present in this node. So we just add here this E and create a new node. Automatically, our creation of the node will be with false, indicating that the word is false. Only after we finish traversing with all the characters through our all characters from the string, only in the end, in the empty children node, will put this true here, which will say that it is an end of the word. Okay, so we need to put F here because we don't have this F and we're just inserting it, and create a new node, and this last node will be marked true, so it will be end of the word or is word. Okay, right, so let's insert another word, for example MLN. As before, we start from the root. We try to understand if this M, the first letter, is in the root children or not. So if it is not, we put it here and create a new node and mark it default false, right? And then we move our current node to the node we have just created. So this is how we traverse through the tree, right? From the root to down. And this will be the same operation when trying to find something or search the word or search the prefix, right? We've created a new node, and then we'll just ask if we have this L here. Okay, we don't have this L, then we create a new one, put the N here, default false, and create a new one and put it true because we just end the word here. We'll do the last insertion here. It will be a very interesting one, and its word will be ABCD. So what we do if we have the same characters, and not only the same characters, but the true in the way down the tree. So you can see that we start with this current node from the root, the same operation. We go from A's pointing node, we go to this node, which children has B, and they go through B's node to C's node, and here we can see that the children of these nodes does not contain this D letter here. So we put D here, create a new node. We see like this is the last letter, so we'll put true. And now you can see that in this line, you have two truths. So it is not mandatory that only truths should be with empty children. No. For example, this node, which contains D, has true, which is indicating that you have this ABC here, not ABCD. So keep in mind that when you end the word, the new node which is created is just something like kind of here, indicating that you have ended the word. So this word exists here or not. So this true will be for C. This true will be for D, etc. Okay. So I think that basic operation of insert is very clear. Of course, you can do it recursively, but iterative will be, I think, much more simply to do. Okay, let me clear this part and we'll try to find some words. And let me write down the words we want to find. So we're now try to understand how search word works and not search prefix. Okay. So for ABC, it is very simple, right? You take this current node, the root one, of course, then you go through all the characters, and when you come up to the last character, you ask if it is a word or not. So it will be something like, so you take this string here, okay? Yeah, then you iterate through all the characters and ask if this character is in the current node or not. So at first you'll take this current node equals to root, not to lose this root pointer, of course, because within your Trie tree data structure you'll have only one root, and if you move with this root pointer or root reference, you just lose it and can't come back. Yeah, so you'll keep this current in the current pointer root and work with current pointer. Yeah, so if you can find this C in this current node children, then you are allowed to go down, right? So we'll check if the current node's children contain this C or not. If it does not, then we'll just return false. And what the case is this? For example, you want to find this BCD, and the root children does not contain this B letter here, so you'll just return false, right? After you just go down with simple manner, as you're just inserting, this is the same operation here, the same kind of operation here. So, okay, the current will go down to its children's C. So this is your steps. This is how you go down, okay? And you can't end up with null because each time you're asking if this letter exists in current children or not, right? So this part won't be undefined behavior anytime. And the last return will be if the current is word or not. Let's just move. Let's just try one example. So the current is root. We'll try to find in the children if it contains this A here. Yes, it contains. So we go to current's children C. So you'll take this hash map. You'll take this C character there and go to the node which is pointing this C character there. Okay. So you go down. The same operation, you go down to C, and once more you go down. So for the last character, you're asking if C, yeah, it's the same letter, but you understand this is just a, it should be CH, for example, here. Yeah, it's just a variable name, this is a character here. So you're asking if C character exists in the current node. Yes, it exists, so current equals to current children C. So the last one, you go here, so current in this line, after this for loop, this is after this for loop, will point to this node, okay? It contains the or does not, it doesn't matter right now. What actually matters is that if it is a word or not. So now you're just returning is word, and you answer the question of search word. For the other example, if you search for AB, you'll end up this current node in this node, which contains C and E. But you are searching for AB, so the main variable which is answering the question if AB was inserted in this tree or not is this F, right? Because you're searching A, B, and this F will indicate if it is a word or not. So in this case, you'll just return false. For the operation of search prefix, you won't have this isWord return statement here because you're just searching for prefix, right? You don't care if it is a word or not. You'll always return true. The only way you'll return false if you can't find the character in some node. That's all. The last one, of course, the delete operation is a little bit tricky. And why it is tricky, I'll just explain to you with two examples. And those examples will be to delete either ABC or ABCD, or vice versa. So we'll look at, does it matter if you delete at first ABC or ABCD? So what is the difference, right? Okay, so for example, you delete this ABC. So what do you think how we do this? Because you have these true in some nodes, and if you have, for example, this ABC word there, you should actually remove this true and mark it false. But what you actually need to do more is to remove some nodes which are actually empty, right? Let's try the easy one. Let's try remove the M, L, and N as we inserted before. So we'll start the same thing. We'll start with current node, ask if this M exists in the current node children or not. Of course, if M doesn't exist in this node, so you just return from delete function and do nothing, right? Okay, so from M you go to L, from L you go to N, and now you see that yes, this word actually exists here because this current node says true. So we see here that true indicates that MLN exists in this Trie tree. This word exists in the Trie tree, and we just can remove this N here and delete this node, right? This is quite simple. You just remove this N and delete this node. And then we'll tell recursively back to the recursion stack saying that, you know, there's nothing here and there's no word here, which is ending with F. So you can remove this one too and erase this L letter here. And the same thing here, it's empty and you just keep removing this M, the last letter, and just delete this node. And now we end up with Trie tree, which does not contain this MLN word. But now the most interesting part. What if we want to remove this ABC here, right? So the same thing, we start with current node root, go to B, go to C, and here we see that it is a word, so everything is okay, we can delete it, but the children of this node are not empty. So what do we do now? You just actually mark this true to false, right? We're just saying that, you know, there will be no more word ABC, but we can't delete this node. We can't remove it from this Trie tree because it is not empty. So there's something which is going down, and maybe there are some other words here. So you can't just remove this one because you'll just automatically delete many, many words there, right? You mark it false, and that's all. And now, if you want to delete ABCD, you'll come to this node, right, from A to B, C, D, and this node, which is indicating this, yes, it is a word. You'll delete this node, remove D, it's empty, it's not a word, delete and remove C, and you are not allowed to delete this node, of course, because its children are not empty. That's all. But now we'll try to delete at first ABCD and then ABC, and you can debug this and try at home, of course. Let me restore our node, our Trie tree. Okay. What will be if I remove the ABCD word first? Okay, the same operations as before. We start the current node, go from A to B, from B to C, from C to D, and we end up with this node, which is saying that, yes, I am a word here. So you see that this is an empty node and you're allowed to delete it, and you remove this one, you erase this D from here, and you won't actually go recursively back and remove this node too, but you are not allowed to do that. Why? Because this node is marked as true, as marked as end of some other node, right? And you can see here that ABC still exists here. You want to delete this ABCD word here, but ABC wasn't deleted yet, right? So you can't just remove this node from here, because you'll just lose the word ABC, right? So your statement, if you are allowed to remove something or not, is not just children is empty. It is empty and is not a word. And you can actually create such a variable like should be deleted, which will be initialized with a return statement in the post order. And your return statement here should be not only if the children of the current node are empty. So you should return current children if the current children is empty and your current is not a word. So going back to this stack, so for example, we had this D here in the previous step. When you come back from D to C, you erase this D and you can come back to C. You're asking, you should be deleted if your current children are empty. Yes, they are empty. And your current is not a word. So here you can see that it is a word. So for this node, when you come back in the recursion stack, you'll just send false here. On the other hand, when you had this M, L, and N, when you erase N from the current node children, you just pass back the current children is empty, and it's actually empty, and yes, it is not a word. So this node is allowed to be deleted as well, and so on. So I think that this is the most confusing part of delete operation, and you should be very, very careful with this is word or not. Of course, you can have some situations, for example, problems you are asked during interviews, and for specific problem, you'll need to have more data members like counts or other things to help you to solve some problem. But this is a very simplified version of trees. So this is a good starting point to get them know. And after that, of course, you can go for the suffix trees. And I suggest you to implement directly suffix arrays because they are much more simpler and support the same functionality as suffix trees. So there's no need to do that, but you can do that, of course. So today we talked about trees, 4 basic operations. Hope it was clear to you. Thanks for watching.